So one of the things that you can do in order to evaluate hemoglobin, or sorry, myoglobin and oxygen binding of myoglobin is to use spectroscopy. The heme group is a very strong chromophore, so that's actually going to absorb UV and vis light, or sorry, visible energy, energy in the visible light spectrum. Now, the ferrous form, Fe2 plus, without any oxygen, has a very intense Soret band at 429 nanometers. And so that's within the visible light spectrum. If you remember, the visible light spectrum is approximately 400 to 700, or maybe it's 450, I can't remember, but that's very close to the visible light spectrum. So you're actually going to be able to see that, or that's actually going to produce a visible color there. Oxygen binding to that alters the electronic properties of the heme and shifts the position of that Soret band to 414 nanometers. So you have a shift of that energy there. Now, binding of oxygen can be monitored by UV vis spectrophotometry for this reason. So deoxyhemoglobin in the venous blood is going to appear quite purplish, whereas oxygenated blood in arterial blood is going to appear red. So there are kind of cues as a result of heme being a very strong chromophore and how it absorbs light. Now, a question, why do you need hemoglobin and myoglobin? Could myoglobin, that monomeric protein, could that ultimately transport oxygen? Well, the partial pressure of oxygen, the P sub O2, that's effectively the concentration of oxygen in the lungs, is approximately 13 kilopascals. Now the units, they're relevant, but they don't particularly matter for the explanation of this example. Now what that means is that if we look at a myoglobin binding curve, myoglobin, globin O2 binding curve, what we have is our P50. We're about 50% saturated at, let's call that, I mean, if we scaled this, that would be like 0.25 kPa, something fairly low. Now, if we look at PO2 in the tissues is 4 kilopascals. Okay, so let's put those points on imagining myoglobin. If myoglobin is put into an environment where the concentration of oxygen is approximately 13, we're talking out here, what percent of myoglobin is saturated? We're talking like 90+% if it's 13 kilopascals. Okay, out there. Now, what percentage of myoglobin is saturated at 4 kilopascals? Well, 4 kilopascals is right there. We're talking like 85% or something like that. So myoglobin, if it were responsible for binding oxygen and then going to a place where the concentration is lower in hopes that it would release it, well, it's not going to do that. It's not going to release it to a high enough concentration, because when you look at these two environments, the tissues versus the lungs, both of those environments have high enough oxygen concentrations that hemoglobin is going to be, well, it's going to be more than 50% saturated. Now, what that means is the P50. So the P50 is an indicator of affinity. So the lower that think about it like this, the lower that the P50 is, then the higher the affinity that protein, that myoglobin has for oxygen. So would lowering the P50, the question at the bottom here, would lowering the P50 of myoglobin to oxygen help? Not really. Instead, raising it, because at that point, if you increased it to say like 10 kilopascals or something like that, say the P50, if P50 was 10 kPa, Well, then at 10 kilopascals, well, 50% would be saturated. 50% therefore would be devoid of any oxygen. So think of, keep this term in mind, or this idea in mind. Low P50 equals high affinity. High P50 equals low affinity. And it's strange to think about this in terms of like, do you want the protein to release the oxygen? But that's the way that you kind of have to think about it. If the P50 was 10 kilopascals, well then, if the P50 was 10 kilopascals and the environment had a concentration of 13 kilopascals, the environment's concentration would get that protein to at least 50% saturation. Now, if the protein's P50 was 10 kilopascals again, and the concentration in that environment was 4 kilopascals, then it wouldn't have a high enough affinity for the small amount of O2 that's in that environment to be at 50% capacity and 50% saturation. It takes a little bit of while to play with this idea, but think about that and think about what the environment provides and whether or not it's going to be at 50% saturation or higher or lower or something like that. So keep that idea in mind as you kind of work through this. So this graph right here shows a couple of different things. And if we look at, let's label these as A, B, and C. And what I want to do is I want to focus on A and B. We haven't gotten into hemoglobin too much, but we will. So A is the curve for myoglobin. That just shoots up. It has a very low P50. It doesn't require a lot of oxygen in order to be at 50% saturation. B, on the other hand, well, it's got a little bit of a different shape. As you notice that it's got a couple of different curves to it. Certainly not a linear curve, but this is known as a sigmoidal curve. Or it has a sigmoidal shape. And the reasons for that we'll get into in just a little while, but what I want you to do is look at that curve for B in two different scenarios. Or two different locations. PO2 in the lungs versus PO2 in the tissues. Okay, so ideally what's going to happen is hemoglobin is going to be in the lungs, it's going to collect a very high concentration of O2, and then it will be moved through the red blood cells, move throughout the body, and then finally when it gets into the tissues, well, what do we see? We see that there's a lower oxygen concentration. And what do we know about this protein, B, and its affinity for O2 at a lower concentration? So we could say that right here, our P50 is approximately like 3 or so. So when our protein has, let's just go ahead and say B has a P50 of, let's call that 3.5. Doesn't really matter that much. What does that mean about, and again, let's think about this in terms of you've got 100 hemoglobin proteins. 100 hemoglobins. If the PO2, so the concentration of oxygen, is 13, then I would say about 90 of 100 hemoglobins are bound to O2. Okay, so what does that mean? That means that 10 of those hemoglobin proteins are not bound to O2. Now let's say that B goes into an environment where the PO2 is about 4. What that means is that of those 100 hemoglobins, only about, let's say, 55 have O2 bound. So what that means is that going from our lungs over here to our tissue, our 100 hemoglobins, they are not, sorry, of our 100 hemoglobins that are in the lungs, they're going to take up a bunch of oxygen. There's going to be 90 that are completely, they've got all of their oxygen bound. And they're going to move through the body, they're going to land in the tissues, and now all of a sudden, only 55 of those proteins have O2 bound. So what does that mean? That means about 35 of those proteins along the way, when they got to the tissues, released oxygen. So now our tissues have been oxygenated. And it's because of this affinity that we see with our hemoglobin proteins. So they had a high concentration in the lungs, a low concentration in the tissues. When they got to the tissues, they were able to release it because the concentration of oxygen in that environment was low relative in the lungs. Now, how can this oxygen affinity, or how can the affinity to oxygen change? Well, in order for that to happen, you have to have a protein with multiple binding sites. So these binding sites must actually be able to kind of communicate or interact with one another. Now, this is a phenomenon known as cooperativity. This cooperativity is, well, I'll get into kind of a metaphor for describing it in just a little while, but what we see with hemoglobin is something known as positive cooperativity. So the first binding event increases affinity at the remaining sites. This is recognized by that sigmoidal binding curve that we saw previously. Negative cooperativity, on the opposite hand, is the first binding event reduces the affinity at the remaining binding sites. So here's our 4 subunits of hemoglobin. 1, 2, 3, and 4. When O2 is absent, all 4 of these subunits actually have a fairly low affinity for O2. But when there's a high enough concentration of O2, that first protein, that first of the 4 subunits of that quaternary structured hemoglobin protein is going to bind to O2. And when it does, it causes protein number 2 to say, oh, well, I want to bind some O2, and it does. Then 3 says, well, 1 and 2 have bound to O2, so I'm going to bind to some O2. And then the 4th one says, okay, fine, if you guys have all bound to O2, now it must be cool, so I'm going to go ahead and bind it. So you have 4 binding sites. The first one is kind of the toughest to get over. That's the toughest kind of barrier to break down. It's the negative energy, basically. Whereas once you get that first oxygen bound, then the remaining ones are going to bind, and now all of a sudden we've got a completely saturated protein. So that's positive cooperativity. Negative cooperativity is the exact opposite. As soon as the first subunit binds to it, well then now all of a sudden the rest of the subunits have even less interest in binding to it. So cooperativity is kind of modeled in this way. So what we have here is a depiction of a protein that is going to bind to its generic substrate or its generic ligand. And what we've got here are these 2 binding sites that are adjacent to unstable regions of a protein. Now, those binding sites are fairly stable, so they're ready to receive that protein, but it's only whenever this first one, so ligand 1 and ligand 2, so when ligand number 1 goes to the binding site, what that's going to do is cause, I'm going to call this polypeptide 1, pp1, and pp2. When the first polypeptide binds to the first ligand, that's going to help stabilize the protein. And stabilizing polypeptide 1 is going to, in effect, help stabilize polypeptide number 2, which whenever polypeptide number 2 is stabilized, now all of a sudden the ability to bind to that second ligand becomes more likely and is more favorable to actually take place. So this is that cooperative, so they cooperate with one another. Now, cooperativity can be modeled, and it's a little bit more complicated and more challenging than what we were talking about previously with that theta representation. And the reason for that is because you have all of these different factors. You have all of these different subunits. So cooperative proteins have multiple ligand binding sites, so our K sub A is changed. Now all of a sudden we have to worry about N, the number of binding sites. So that N value finds itself there, and it finds itself there. But we rearrange that K sub A to meet this theta, or to be displayed as theta, and so theta is equal to L to the nth power divided by L to the nth power plus K sub D. Now that can be rearranged to make what is known as the Hill equation. Now the Hill equation is log of theta over 1 minus theta is equal to n times the log of L minus log of K sub D. Now what this does is basically takes all of this sigmoidal, so this otherwise sigmoidal curve, and kind of linearizes it. Now n is the Hill coefficient, so this is the degree of cooperativity. Now if that cooperativity is equal to 1, there is no cooperativity. If n is greater than 1, that will be a positively cooperative protein. Now, if n is less than 1, then that's negatively cooperative. So whenever you're plotting the data for the binding of a protein and a ligand, you can see whether or not there's cooperativity. If it's a n equals 1, there's no cooperativity. If n is less than 1, that's negatively cooperative protein. Now, what this actually looks like is right here. So what we have is a couple of different things to look at. We have myoglobin. Our n sub h, or our n, is 1. So what does that mean? No cooperativity. Now, hemoglobin, and we'll get into this a little bit later, has a couple of different states that it exists in. It has its low affinity hemoglobin, where n is equal to 1. Again, no cooperativity. And then hemoglobin in a high affinity state has an n equals 1, but then hemoglobin, whenever it's saturated, has an n equals 3, which 3 is greater than 1, so it is positively cooperative. Now, what this graph looks like, and we'll get into this in a little while, positively cooperative, is that hemoglobin undergoes a number of different changes from a low affinity state to a fully saturated state. We'll get into that in, I believe, the next video, but the Hill plot gives an idea of cooperativity, and it can be valuable in looking at different states in which a protein is. So this could be something that you change based on an environmental factor. In this case, we're talking about a protein undergoing significant conformational changes, though. All right, I hope this is helpful. We'll be continuing on in just a moment.